Okay, 15.6. Okay, it has a lot of material in it. And first thing we're going to do is talk about directional derivatives. Okay, these are derivatives in any direction. So, for an example, let's let our function represent temperature. On a flat metal plate, at a point xy. Okay, so here's my plate. Let's make it smooth, doesn't matter, but that looks more like a plate. Here's my point. Let's say here's an axis so I can compare it to. And if this point is xy, let's move over by h. This point is x plus h, y. And this point goes right to f of xy. And this point goes to f of x plus h, y. And since F is temperature here, that represents a change in temperature, then T of x plus hy minus T of xy is a change in temperature as the point moves from P xy to x plus h y. And if we divide this by h, this represents the average change in temperature with respect to distance as the point moves in the horizontal direction. And if I take the limit, which is the partial with respect to x of that, then I get the actual rate of change. As point moves in the horizontal direction. And if I do dy and let y change, then I get the rate of change as the point moves in a vertical direction. So I have a derivative defined as the point moves horizontally, and I have one defined as it moves vertically. But what if I move any direction? So that's what I'm going to do next. So let Q be any other point on the plate. So here's P, here's Q, and let R be this point. So I'm just moving a little bit away from X and Y. And I'm not moving vertical or horizontal, moving both. So here's the vector PQ, and let R be right there. So now I'm moving in any direction. Then I'm going to let delta Z in this case, that's delta T, change in temperature. So this will represent the difference in temperature between the point P and R. And if I divide that by the distance between P and R, or which is delta Z. Let me fix this. Then what that represents is the average temperature change. That's just like dividing by h, the distance between them. And then if I apply the limit, as the distance goes to 0, as those points get closer and closer, then I get the actual rate of change with respect to the distance between P and R in the direction of PQ. So this gives us a directional derivative. Now let's put this in terms of unit vectors. So my direction I want, say, is along this line L, and P is the point I start out, and then let's just do a unit vector, so the length is 1, and U, let's say, is U1I plus U2J, where U1 is the horizontal component and U2 is the vertical component. So this is the unit vector from P along L. So that is going to give us our direction. If we do any point along L, then the vector PR, we can say, is some scalar times the unit vector. That's just going to give us its length, because it's the same direction as U, and it just might be longer or shorter. So that makes R to be x plus t U1, y plus t U2. And that makes delta Z f of these values. And t is the distance between P and R. because it's either stretched or shrunk by t units. So when we get delta z divided by the distance between those two, that's just like dividing by h. We have this. Again, that's the average change in f at the point P in the direction of u. But if we take the limit of that, as t gets smaller, then that's the actual rate of change. At the point P in the direction of u. Now we can take a derivative in any direction. So we can write down this definition. A directional derivative of a function at a point P in the direction of u, where u is the unit vector, we'll write as du f of x, y. We're going to say that's the limit as t goes to 0 of all that above. u1 and u2 are the components of u, remember. Okay, then we have a theorem. If f is a differentiable function of two variables and u is a unit vector, with u1 and u2 as its components, then the directional derivative of f is fx xy u1 plus fy xy u2. So that's going to be important. So let me do an example here. Let's say our function is x cubed y squared, and my point is negative 1, 2, and my direction, well, that's not a unit vector in this case. The direction you want in are the same as the vector for negative 3. Okay, so the first thing I would do is find u, the unit vector, for the direction, and the length of that vector is 16 plus 9, square each one. That's 5, so our unit vector is 4/5, negative 3/5. That's u1 and u2. And now we take partial of f with respect to x, so y is constant, f with respect to y, and we say du of f is this. And if we want that at the point, negative 1, 2, then we just plug it in. And we get 12. Okay, another way we can write the directional derivative is as a vector dot product. So that's the same thing. So a definition, if f is a function of two variables, then the gradient is equal to del f fxi plus fyj. And we say that that's del. So we upside down triangle f, you say, is del f. And another way we can write du then, the directional derivative, is the gradient dotted with u. So this is another important part of this section, is knowing what a gradient is. So you could just write del as an operator, operating on a function. So if you do del f, that's going to operate on f, and these here, the partials will be on f also, since you're operating on f. Here's an example. We want del f at the point 3, -2, f of x. Oh, excuse me. F of x is 2x minus 4y. F with respect to y is -4x. So del f is this. At the point 3, -2, it's 14, -12. You just plug those points in. Okay. Then it says find the directional derivative at that point in the direction of the vector from 3, -2 to 4, 1. So first off, let's call it w. We got to find that vector, so that's going to be 4 minus 3 over 1 minus 2. Remember, you take the tail and subtract the head from it. So that's going to be 1, 3. And then to find the unit vector, we divide it by its length, which is square root of 10. So the unit vector we're going to use is this. Remember, the directional derivative is a gradient dotted with u. So that's just going to be 14 minus 12 dotted with 1 square root of 10, 3 square root of 10. Which is going to be 14 square root of 10 minus 36 over square root of 10. It's negative 22 over square root of 10. Now, what does that mean? Well, if the function is temperature on that plate, and du of f at that point is negative 6.96, which is a square root of 22 over 10, it's 22 over the square root of 10, then if a point moves along w, or that unit vector, the temperature at that point P, which is 3, -2, is decreasing because it's negative at approximately 6.96 degrees per um, unit, 1 unit chain. It's supposed to be 1 unit change in distance. So we have a directional derivative starting at a certain point, moving in a given direction, and we can tell the change, the rate of change. Okay, here's another theorem. Like I said, there's a lot of information in this section. We can show, and I'll prove this, that the maximum value of the directional derivative at point P occurs in the direction of the gradient. And the maximum value is equal to the magnitude of the gradient vector. So the proof is real simple. We know the directional derivative is a gradient dotted with the unit vector. This is also the magnitude of the gradient dotted with, or times, the magnitude of u cosine theta, where theta is the angle between u and del f. Well, the magnitude of the unit vector is just 1, so we have that. Well, this is a maximum when cosine theta is 1. And that means theta is 0, so u has, that unit vector has the same direction, or they both have the same direction as the gradient. There's no angle between them, so they have to have the same direction. And then the directional derivative is the magnitude of f, because this cosine theta is 1. So that part disappears, the red part disappears. So that's pretty easy to prove. Okay, so let's do an example here. Okay, and it says find the direction f most rapidly increases at the point 3, -2. Well, we already found the gradient at 3, -2. That was in our other example, and we got 14, -12. So this is the maximum rate of change in this direction. And the magnitude of the gradient f is the maximum value of this change. Okay. Okay, the second part I'll do in a separate lecture, the second part of this section, so we'll do this in part two since it's so long.